Okay, so well, I didn't quite finish typing the lecture notes up, but on Tuesday I promise you really will get them. So you have to do the writing yourself today. So, as I said last time, the first topic that I want to discuss, well, it's a bit hard to find a good name for it, but I'll call it the subject of energy flow. And there's a number of sort of biological questions, or a large number of biological questions that just have to do with how energy flows through a biological system or through a cell. And the first type of biological question has to do with the general problem that why is it that despite the fact that there is so much thermal effects going on in a cell, everything moves around like crazy at these small scales due to thermal fluctuations. Why is it that despite all that noise, there is still order and structure in the cell? So where does order in the cell come from? And one very important ingredient there, of course you know that, I've mentioned that also last time, is that a cell is not just a cell is not just a bag with soup in it. There's a lot of structure in it. And for instance, the nucleus is surrounded by some membrane, and that membrane is not doesn't allow anything to just pass through. It is very selective to the types of molecules that it can go through. So here a very important ingredient is the topic of membranes, and in particular the effect of osmosis. Yes. And osmosis is a typical sort of thermodynamical phenomenon that we'll discuss in the context of this first chapter. So this is roughly speaking, the first type of question that I want to answer. There are many other questions which fall into this category. We'll see a bit more of that as we go along. The second type of question which we'd like to answer is about reaction rates. So reaction rates, with reaction rates, I really mean reaction rates in a very general sense of the word, both mechanical and chemical. So for instance, what you should be thinking about is the reaction rates which are involved in building structures inside the cell. So for instance, if you have some large, so let's say a microtubule inside the cell, it's a protein structure, and it consists of all sorts of building blocks which are stacked together like this, and these structures can grow as a function of time. And the question is, how does such a structure, how does that manage to grow? So how does, if you have a soup of other protein building blocks floating around there, how do they attach, and at which rate do they attach to this larger structure, and what determines that particular rate? So if there's a particular rate for such a protein to attach to the larger structure, but there's also a certain rate for this to detach. And there is some balance between the two, and if the rate of attachment is larger than the rate of detachment, then the structure will grow. But if the rate of detachment is larger, then the structure will shrink. And the question is, what sets this rate? What sets the attachment and detachment rates? a related question is, of course, how does that all depend on temperature? If you increase the temperature, will it go fast? Will it grow faster or will it shrink faster? So how does this depend on temperature? That's a very important question. Of course, biological systems, or at least in the human body, the fact that we're all at roughly the same temperature is very important. And if you would raise your temperature a little bit, then all sorts of reactions go very wrong. So temperature clearly plays a very important role. So that's about the second question. And of course, chemical reactions also fall in this class. There are many chemical reactions which play a role there. You also typically have, as it is called, a forward and a backward reaction rate. So if you have some chemical reaction, A plus B going to C, then typically, where A and B and C are some chemical substances, then typically you also have a reaction which goes the other way around. So this is called a forward rate, and the other one is a backward rate. And it's the balance between the two that determines how much of A and B and how much of C you will have in a particular setting. And again, you would like to know how temperature influences those reaction rates, those equilibria. So it's a very wide topic, and it falls in this under the category of these thermodynamical problems. Okay, so the third thing I want to discuss, maybe I should write it here. The third topic has to do, well, there's not really a very simple, well, there is a simple intuitive picture which I will give in a minute, but the technical word which is associated to is depletion forces. These are microscopic forces which are very important when you have systems where thermal effects play an important role. And I'll just illustrate that a little bit at the level of a drawing. So suppose I have some big container with a lot of small molecules dissolved in the fluid. So these are small ones, and they move around thermally. And suppose now I have a bunch of larger molecules present as well. And these small ones, if the density of these large molecules is large, then the small ones can go anywhere, and they will just kick these large molecules, and they will, since there is on average as many in a direct neighborhood on any position of these large molecules, they will feel roughly the same force. So on average, they will not move. They will of course fluctuate thermally also, but apart from that, nothing much happens. But now if you move these large molecules closer together, or these large proteins, such that these small ones can no longer penetrate in the space between these large molecules. So these small ones, they can only get here, but they cannot get in between. Then clearly this force which these small molecules exert on the large ones now only acts from these sides, but it no longer acts from the left. And similarly for the other molecule, essentially there is a component of the force missing which would push it, which would act on the right-hand side of it and would push it to the left. So in this kind of situation, there's an attractive force, an effective attractive force, because it's essentially the molecules around it which push it. And this attractive force is what is called the depletion force. So it has to do with the fact that if you bring large molecules in a solution of smaller ones, if you bring them close enough together, then the space between them at some point becomes so small that there's no way for the small molecules to sit in the middle and to push them away from each other. So there's a small but very often non-negligible attractive interaction, and that's called this depletion force. And again, we would like to know, well, as I said before, what is the role of the temperature in this process, and how does this depend on the radii of these molecules. These are all questions which you can settle with thermodynamics. Okay, so it's fairly basic material. There's no real large organism playing a role here. This is all sort of the building blocks of biology, but we'll have to start somewhere. Okay, now let me see if I can manage to erase this in one shot. Brilliant. So as I said, the main ingredient in this story is thermodynamics. And before we go into sort of the nitty-gritty of that, there's one sort of topic which comes back so often in thermodynamics that we should spend a single board on it. You've probably seen most of this before, is the topic of ideal gases. So experimentally, of course, it's observed that if you have a gas which is sufficiently dilute, then there's a number of laws which apply to that. You have the law of Boyle, which essentially says that the pressure times the volume is a constant if T is constant and the number of particles is constant. So it gives you this typical PV, these type of graphs. Then you have the law of Gay-Lussac, which is similar, but now about the things happening at constant volume. So Gay-Lussac tells you that the pressure over the temperature is a constant. If V is constant and N is constant. And then you have Avogadro's law, which tells you that the volume over the number of particles is constant, provided temperature and pressure are constant. And well, you've probably seen all this before. The upshot of this story is that if you combine this all together, that the pressure times the volume is equal to, or is proportional to the number of particles times the temperature. And the proportionality, so there's one proportionality constant, and that's Boltzmann constant, K sub B. And that's some small number, well, to be precise. Sorry, that one. So Boltzmann's constant. Of course, these numbers at this point don't play too much of a role, but minus 23 meters square kilograms per second per Kelvin. Is there anybody who has problems verifying, I mean not now in your head maybe, but problems verifying that this type of relation is dimensionally correct, that the dimensions work out, or should I spend some time explaining that? Yes or no? Votes, please. No. Good. Okay, so Um, this is a very small number, and that number comes back over and over again, and everything seems to be right. These laws are, well, of course, originally discovered in an empirical way. You can now derive that from statistical mechanics, but it's a bit of a bore, and we don't need that for biology, so I'll just stick to this as an assumption. We'll take this to be true. For ideal gases, so you need to have a suitably dilute gas, otherwise this doesn't work anymore. Essentially, what is important here is that the molecules in that gas do not interact with each other, or interact only very weakly. The second ingredient, so this is the first ingredient which we need. The second ingredient of an ideal gas which we need is that the average kinetic energy of a single molecule is equal to 3/2 times Boltzmann's constant times the temperature. And again, you can derive this from statistical mechanics. You can see it in Nelson's book, but it's not very important for us to know how you can derive it. So we'll take this as an assumption. Maybe we'll get back to it later. So whenever I'm now going to discuss things, I will keep coming back to this ideal gas, simply because it's the simplest gas that you can think of, and many concepts can be illustrated very well with an ideal gas. Very often the interactions between the molecules of a gas are not very important. Okay. So let's now go into some more interesting topics. I'm very curious how this is going to come out, this recording. Okay. So, well, as you see in these formulas, and of course, as you know, I've already said many times before, temperature plays a very important role. But temperature is a sort of concept which is only useful if systems are in equilibrium. If you have two systems next to each other which don't have the same temperature, then they will typically talk to each other, and if they're not isolated, and so you will not have a stationary system, and therefore temperature is only useful for equilibrium situations. And in order to describe what's going on with non-equilibrium situations, we need to know a little bit more. Now, we know one property of a gas, independent of, or a gas or a liquid or any thermodynamic system. One useful property, which you can always define even if you're not in equilibrium, is the energy. So the energy, that's what is called the state function. In a sense that you can define it independent, so you can compute it independent of whether or not you're in equilibrium, or if you wish, you can measure it always. And it doesn't depend on what your system has done over the course of time. If I give you a system, you can do measurements and you determine its energy. So it's a state function. We'll get back to that concept of state function in a minute. Now, energy by itself is not really enough to determine whether or not a system is in equilibrium. So consider, for instance, two slabs of material connected to each other. This is at the temperature T1. This is at the temperature T2. This has some energy E1. This has some energy E2. Well, let me remove these temperatures, because as I told you, we're not going to talk about equilibrium situations. So this segment has an energy E1, and this has an energy E2. And the question is, are these things in equilibrium? Now, of course, you cannot answer that question, because clearly I can put a coin on top of the Eiffel Tower, and whether or not they're in thermal equilibrium, I cannot tell, despite the fact that I know their energies. So energy by itself is not really enough to determine whether or not systems are in equilibrium. And of course you know that because this is only one of the many parameters that you need to describe the properties of a gas. For instance, if you think about these two systems as containers filled with gas, so let's generalize this a bit. So I have here some container at E1 with some gas molecules which are moving around under the influence of thermal effects. Here you have a second one, perhaps a different density, whatever, some system which has energy E2. And we put this whole thing in some isolating box so that no energy can go in and out of the system. So the total energy is constant. So E1 plus E2 is constant. Then just specifying the energy is not enough, because there are many microscopic states, many ways in which you can distribute these particles, in which you can give them velocities and positions, which are compatible with this constraint that the left-hand side has total energy E1 and the right-hand side has total energy E2. So there are many microscopic states which are compatible with the macroscopic conditions. And so it's not such a surprise that you need to know more than the energies in order to say something about whether or not these are in thermal equilibrium. Okay. I'll go here. Now let's look at a system which is slightly simpler than that system there. So in order to introduce the concepts which we need. So here's a simpler system. Consists of some box with a bunch of molecules in one corner, gas molecules in one corner, and nothing else. So the other space is empty. And this is at some fixed temperature, and there's some fixed energy stored in these things. It's in an isolating box, so no energy can go in or out of the system. And well, as I said, if you know the total energy, you still don't know whether it's in equilibrium. But you do know, of course, intuitively that these molecules, if they move around, they will eventually spread to fill the whole box. So this will go to a situation where these molecules, on average, will be found anywhere. A bit more precise way to say that is that if you observe these systems for some time, so you do some measurements of the set of positions and the set of velocities at some time t equals t0 and then some later time and so on. If you do that here and these time steps are relatively small, then you will of course find that these positions are all restricted to be sort of close to this corner. So there's a certain order in these measurements. These positions, let me call this system 1 and system 2. The positions in system 1 are in one corner. And so if you do a number of measurements, these measurements show a certain order. Or structure, if you wish. But order is the more appropriate word in this context. If you do that same type of measurement here, so if you do a repeated number of measurements in the system down here, then you can find these positions to be anywhere. So there's much less order. If you want to make a prediction about what type of values you get for the velocities and the positions, then you will have absolutely no prediction for these positions, because these molecules can sit anywhere. Where in this case, you know something about the positions. The positions they're all restricted to the smaller subvolume. So this system 2 is, as we call it, a system which has a larger disorder. So if you wish, the disorder of system 2 is larger than the disorder of system 1. Measurements in system 1, as long as you do them before the system has gone to system 2. So measurements in system 1 show much more structure, much more order, because the x positions are never, of the molecules are never in this part of the box. So clearly, without specifying this any further, without specifying the interactions between these various molecules, we can sort of get the intuitive understanding that it will be useful to have a quantity like energy, but now which says something about the disorder of the system. Okay. We'll get there in a minute. What is important here also is that experimentally we see that systems like this always evolve to systems like this and never the other way around. So that's something which is called, well, it's an experimental observation. It's something which you never see it happen the other way around. It's an empirical law, and it goes under the name of the statistical postulate. Which says that if you leave a system to evolve for a sufficiently long time, it will always evolve to a state of maximal disorder. It will go to a state of maximal disorder. That's something which you see on your desk. If you wait for long enough, it will become a mess. That's the statistical postulate. So this is sort of a formal way to say that these molecules which sit in a corner, they will not stay there. They will move around in a box and they'll spread out. And I have to be a little bit more precise about what I mean with this word state. This maybe I should should say this in a more in a slightly different way. Let me erase one more board. So a different way to say this, or which is maybe more precise, is, so instead of this part, we'll go to a state of maximal disorder. I will use a different formulation and say it will go to equilibrium, where equilibrium is not just a single state where all the positions and velocities of the particles are fixed, but it's an ensemble of microstates which is such that that ensemble has the maximal disorder. So equilibrium is an ensemble of microstates where by microstates I mean that one particular set of positions and velocities for these molecules. So equilibrium is an ensemble of microstates with maximal disorder. So that if I do a measurement, I have least information about what the values of this position and velocity measurements will be. So this word state here is really a macroscopic state. So macroscopic state is a state which is labeled by a few of these parameters like energy and disorder, whereas a microscopic state is a state which is labeled by all the positions and velocities of these molecules. Okay. Any questions about that? So now comes the time to make this disorder a little bit more specific. So this macroscopic parameter which describes the disorder, similar to the macroscopic parameter energy, which says something about the total energy of the box. This parameter disorder is called entropy. And entropy is formally defined, it's always denoted by an S, and it's formally defined as some constant times the logarithm of the number of microstates. So this is entropy. Kb is the Boltzmann constant again, and this is the number of microstates. And of course, it's a number of microstates compatible with the external parameters which you keep fixed. So if I talk about the number of microstates of this system 2, for instance, then it's a number of microstates compatible with the fact that we are at a certain temperature, that the box has a certain volume, and that there's a certain total energy stored in this system. This constant Kb here is totally arbitrary. You could have put in anything else here. It's not really relevant. It just makes these numbers somewhat more manageable, because typically this number of microstates is very large, and if you then multiply with this very small number Kb, you will still get something manageable, but we could have put anything there. It's not important. The logarithm is important though, and the logarithm is, so you can understand it intuitively where the logarithm comes from by thinking about, I erased the wrong board. This is very bad that you cannot go back. Okay, I'll draw this again. The logarithm is, you can intuitively understand by thinking once more about these measurements which you do on a box. So suppose, so this is all about the logarithm, why there should be a logarithm in there. So suppose, or why it makes sense to put a logarithm, it's not the only thing you could do, but it's a natural choice. So suppose that I have some system which has capital N molecules. And suppose that these capital N molecules can each sit in N states, different states. So roughly speaking, if you have, you could think about very simple systems where you have some spin which you can be up or down. But of course, this can be a this number of states can in principle be a continuum, can be an infinite number. Let's for simplicity think about a system where you have only a finite number of possibilities. So for instance, this N states labels the number of positions available to our molecules in the original box. So the one I just erased. Here, the number of positions which are available to these particles, this N states, will clearly scale like the volume of the box. If you make the volume twice larger, then there are twice as many places where this this particle can sit. And so suppose we have such a system, and capital N molecules, small n number of different states for each molecule. Then if you would want to describe, well, if you want to compute the logarithm for the entropy of this system, you would get that S goes like the logarithm of n of small n states to the power capital N. I mean, for every particle in that set of capital N ones, I have to choose choose which state I'm in. So the total number of states is this, and this is equal to, or it scales linearly with the number of particles by the property of the logarithm. Now, what this formula really tells you is that if you want to construct a number out of this configuration, if you want to label this configuration by a particular number, that you need capital N digits, so to speak, to describe this particular state. So what this formula is trying to tell you is that to describe a state, you need capital N digits, where each of these digits runs from 0 or from 1 to n states. This is supposed to be 2. Right, so think about a two-state system. If you have a two-state system, then such a label. So suppose I have molecules which can only be in 2 different states. I say spin up and spin down. So I have a number of them, and this one is spin up, this one spin up, this one spin down, this one spin up. There you have a total of n of them. Then in order to describe this as a number, I can write this as 1, 1, 0, 1, a 1 for a spin up and a 0 for a spin down. And clearly I need n digits to describe what this state is. It's a very simple statement. So S, the entropy, describes that has a log, because in that case the entropy is related to the number of bits, or number of digits that you need in order to describe a microscopic state. Okay, so now that we know what entropy is, we can reformulate this statistical postulate, which I just erased on the middle board, in a different way. So instead of writing this statistical the statistical postulates, we can now go to the second law of thermodynamics. Which says that if you leave a system alone, if you don't exert any external forces on it, then it will eventually settle in a system left alone for sufficient time will settle in the state of maximal entropy. And that's in a way a thermodynamical analog of the statistical postulate. The statistical postulate tells you that what happens with these individual molecules, and now we have formulated that in terms of this single number entropy, which is again a state function. So I should say that maybe once more. Entropy is a state function, just like the energy. It's something which you can compute. If I give you a system, you can compute what the entropy is, and that's it. And it doesn't depend on what kind of things you've done to the system before you started measuring. It's just simply a quantity which you can define for any particular system that I give you. And the second law of thermodynamics says something about this evolution of the system in terms of the entropy. Now, there's one important aspect of entropy which is different from energy. Entropy is not conserved, or if you wish, not constant in time. It's different than energy. Energy you can fix. If you don't let energy go into a system or out of a system, then it will stay fixed. It can change from kinetic to potential energy and so on, but it will total energy will stay fixed. Entropy is different, and entropy will simply increase until it reaches that value of maximal, where you have maximal disorder. So entropy is not a conserved quantity, and that will play an important role in when we actually start computing things. Okay, let me see. What's that time? A couple more minutes. Okay, so let's try to reformulate this second law of thermodynamics in a little bit more mathematical way. So the statement, so let's go back now to a system where we have two compartments like I drew before. So we have a compartment A and a compartment B. The whole lot is isolated, so no energy goes in or out. And so you have some molecules here. There's a certain energy EA in this box. You have molecules here. There's an energy EB in this right-hand side of the box. And we'll separate them, except for the fact that we allow them to exchange energy. So these molecules here, they can hit on this small membrane, which I've put here in the middle. And these fluctuations can transfer energy from the right to the left or the left to the right. But that's the only thing that we allow. So we won't allow for any particles to go through this door. Only energy can go through. And now the question is, how do we describe how this system, how do we describe this second law of thermodynamics? Well, each of these boxes has a certain entropy associated to it. And there's a total entropy associated to these things. So S total is a sum of the entropy of the left-hand side and the entropy of the right-hand side. Again, the fact that I can simply add up these entropies has to do with the fact that we have this logarithm in the definition of the entropy. And we have a total energy E tot, which is the sum of the energy in box A and the energy in box B. And the second law of thermodynamics says that in equilibrium, the entropy, the total entropy of the system, has a maximum. So S tot in equilibrium, S tot has a maximum. Now, since the only thing that you can do is let these systems exchange energy, the only free parameter which we have is, say, the energy in box A. Because once you know the energy in box A and you know the fact that the total energy is constant, you know the energy in box B. So the same, a different way to express this is that the derivative of the total entropy with respect to the energy in box A is 0. That's what it means for S to have a maximum at that particular value of EA. So there will be some value of EA for which this system is in equilibrium, and at that point this expression holds. Now, using these relations, it's easy to verify that this is equivalent to saying that ds A by dEA minus dsB by dEB equals 0 in equilibrium. Okay, now we'll get back to that in more detail next time, but let me just give you a small preview of that. This relation here, together with the idea that temperature should describe equilibrium situations, moreover, temperature should be well defined for this total system once it has reached equilibrium. So if I let these systems exchange energy, at some point we will reach this state of maximal disorder, and at that state you also expect that there is a concept of temperature which you can associate it to this system. This suggests to define temperature by taking the temperature of box A, let's say, to define it as the inverse of the derivative of the entropy with the entropy with respect to the energy. Now that's a very sort of strange way of defining temperature, non-intuitive way of defining temperature. We'll see in the next lesson that this indeed makes sense. And the advantage of doing things this way is that it gives you some quantity which is defined independent of whether or not you're in equilibrium. It's much easier to deal with this type of object. And it's now defined purely in terms of the state functions S and E. And that has a lot of advantages when you discuss non-equilibrium situations. Okay, so we'll take it from there next time. Are there any more questions? Is there too much material which you've already seen? Or is it too weird or too slow? Should I write more? If you have suggestions, let me know.